Okay, good afternoon. It's time to start afternoon session. My name is Woon-Tack from KAIST, Korea. I'm session chair of this session. We have a poll presentation today. Fortunately, all four presenters are here. We don't need to worry about the Zoom connection issues. First presenter is Jinseok from KAIST. His presentation title is a submission. Let's see. His title is Crowd Data-Driven Artwork Placement in Virtual Exhibitions for Digital Density Distribution Planning. Let's welcome the first presenter.
Hello, I'm Jinseok from UVR Lab KAIST under guidance of Professor Woontack. I'll begin the presentation of the study Crowd Data-Driven Artwork Placement in Virtual Exhibitions for Density Distribution Planning. So you might have this experience when you go to this famous artwork. So in real-world exhibitions, visitors often face the traffic congestion and bottlenecks, and this leads to mitigation in experience and engagement with the exhibition. So to cope with this challenge, exhibition designers designate the areas of the artworks not just by the size, but also their popularities. So, and with the emerging concept of metaverse, a multitude of users can engage with content simultaneously in VR and MR-based exhibitions. And the equivalent challenge lies in here too. To resolve these challenges, the researchers proposed approaches including network throughput management, space segregation, and avatar adjustment, as you see on the right-hand side of the slide. However, these approaches cannot effectively address the challenge in the larger context of virtual exhibitions that encompasses AR and MR, as users' physical movements and appearances are inevitable. Therefore, scene management at the virtual space level can effectively address this challenge. To this end, in this study, we propose a novel crowd data-driven optimization of artwork placement in multi-user virtual exhibition for density distribution planning. Before designing the approach, to derive vivid requirements from experts and to validate the efficacy of the approach, we conducted 2 preliminary studies. And through the preliminary studies, we elicited design considerations which are further integrated into our move actions and score functions of the optimizer. With eight exhibition professionals, we raised the questions to derive shared consensus of individual opinions upon requirements of the approach. To summarize the notable results, all participants unanimously agree that the viewing time and popularities of artworks are proportionate to area that artworks occupies, and also they emphasize the importance of exhibition narratives. Exhibition narratives also should be taken into account when planning the exhibition. And to ascertain that artwork relocation indeed disperses the uneven concentrations of users, we carried out artwork relocation experiment. To facilitate the artwork relocation, we devised a bubble-like visual aid UI, as you see on the middle side of the slide, and which represents the required areas of artworks based on popularities during the exhibitions. And with this bubble UI, our client curator relocated the artworks for the pause condition, as you see on the right-hand side of the slide. After collecting visitor data during the virtual exhibition, the relatively normalized value, BA, is calculated based on size, viewing time, and ratings of each artworks during the exhibition. And with this BA value, a diameter of required area, bubble, is of each artwork's DA is determined. To evaluate the uneven concentrations of visitors between pre and post conditions, we devised a heat map metric called user intensity per cell, UIPC. UIPC is a metric for each heat map cells that denotes the cumulative time users spent within designated area, the segments in the exhibition spaces. And we posit the below postulation of correlations between UIPC distribution and crowd density distribution. Please refer to the paper for the detailed postulated analysis. F-test revealed that the post condition had a lower variance of UIPC distribution than that of the precondition in the experiment. And with the postulated analysis, the results indicate that variance of UIPC distribution was lower in the post condition. As you see on the graph, the blue dots are more oriented to the average, whilst red dots are more deviated from the average. Thereby, there are less uneven user concentrations in post condition. As you see on the right side of the slides, there's less sporadic concentrations in post condition compared to the precondition. And this leads to the interpretation that relocating artworks distributes the crowd density more evenly. So with the results and the insights, we elicit the design considerations which further integrated into our optimizer's move actions and the scoring functions. We could confirm that there's a pressing need for automated placement. Therefore, our optimizer adaptively scrutinized the scene with the scene to find optimal placement. And we also designed the 3 score functions with the results of the results and insights. To support this, the process of the optimization consists of the 4 main steps. First of all, we collected the crowd data of 48 participants for the implementation with the 2 medium scenes. And with this crowd data and artwork and space information are integrated into scene data to facilitate the efficient spatial exploration during the optimization process. So reflecting design considerations, 3 scores are used to evaluate the solution scene during the optimization process. The optimizer evaluates the density distribution score with the UIPC distribution based on the aforementioned postulated analysis. Please refer to the please refer to the paper for the details. And to alleviate the potential biases in physical distances between artworks, to preserve the uniform spacings between the artworks, as you see in the middle of this slide, the optimizer evaluates the regularization score with the variance of distances of neighboring artworks. And to keep the clusters of similar artworks, the optimizer evaluates the to keep the clusters of similar artworks to preserve the exhibition narratives. The optimizer evaluates the artwork similarity score with WCSS of clusters of similar artworks, which are commonly used in K-means and K-method algorithm. And with the scene heat map and data, our optimizer explored the scene with these 5 move actions. As you see on the left side of the slides, the figure itself is self-explanatory for move actions. The actions relocate the artwork, relocate the objects, and flip the words. And MCTS algorithm was employed to find the optimal action paths for the solution scene, while searching for the paths with the highest potential, move actions are executed in each step of the tree. For the implementation, we set the 2 conditions of optimization results. The numbers behind the conditions denote the weights of the score set, each score set. So 910 refers 90% of density distribution score, and then 10% of regularization score, whilst 505 is considerations of half on density distribution and half on artwork similarity score. So 910 is a set for exhibition scenarios where clusterings based on similarity is considered, whilst is not considered, whilst rationality of the scene is in considerations. And condition 505 is a set of the exhibition scenario with considerations of clusterings based on the artwork similarity, but without the considerations of rationality of the scene. Sorry. And as you see on the right side of the slide, that's how the optimization process works. The optimizer explored the exhibition space throughout the process of the Monte Carlo research. So according to the numeric figures reported in optimization results, 910 received the lowest UIPC variance, and 505 received the lowest WCSS in both museum scenes. And to envision the qualitative visual inspection and analysis for the scene views, as you see on the red box, condition 910 and 505 chose different strategies to disperse the density distribution, whilst 910 flipped the word to drastically distribute the density, as its major goal is to distribute the density. However, condition 505 chose to gather the artworks together to make the cohesions between the artworks. And as you see on the purple boxes, since 910 had the considerations of scene rationality, it preserved the uniform spacings between the artworks. However, as you see, the bottom part of the purple box, condition 505 failed to preserve these uniform spacings, and there were empty words without the artwork objects. However, there was tendency to preserve the clusterings between the artworks. So based on the artwork metadata, the condition 505, the optimizer preserved the uniform clusterings between the artworks. So conclusively, comparison analysis between the optimization results confirmed that the optimizer fulfilled the intended purposes, and our optimizer provides versatile and effective resolutions in resolving various practical scenarios in exhibition planning. And that's the end of the presentation. Thanks for listening.
Any question, comments, or critics? It's not so easy to make a question just after lunch.
Oh, yeah, okay. Please.
Go ahead.
Hi, Florian from Lancaster University. Thanks for the talk. I was wondering, does this system only work for virtual exhibitions, or is it also possible to somehow apply the same technique to a real museum?
Real museum?
Yeah, to a real world exhibition.
As long as we can get the crowd position data, I think the optimization approach itself can be applicable for the real-world settings, but also AR and MR settings, as in AR and MR setting, it's relatively easy to get the positions of the objects, not objects, but positions of the users, positions of the visitors. But in the case of real-world settings, it's quite hard to get the aggregate the positions of the users. So if we solve that problem, I think the optimization approach itself can be applicable for the real-world settings as well. Thank you.
Hey, thanks for the talk. I was wondering if your algorithm considers other aspects of the artwork, like popularity or other things that might attract people to the artwork.
Pardon me, could you maybe?
Yeah, does the algorithm take in as input any other details about the images, like what the artwork is, or popularity of the artwork and things like that?
Yeah, let me move on to the slides with the artwork data. Yeah, for this study, we considered several metadata of artworks, but in this case, to calculate the similarities of the artworks, at this moment, we only consider the artworks color and artist. But mainly artists to calculate the cohesions of clusterings. Yeah, but I think in future research, to calculate the similarities between the contents objects and artworks, I think much more metadata should be taken into account.
Thank you.
I hope that satisfies the answer.
Okay, let's thanks again. Let's move to the next presentation. You have to prepare. The title is RoomRecon, high-quality textured room layout reconstruction on mobile devices. This paper will be presented by Seok Kim from Maxt in Korea. Maxt is one of the promising AR company in Korea. Let's welcome the presenter. You are ready?
I'm getting ready.
Okay. Yeah, Maxt is well known for the tracking inside and outside of the world. They are actively working on the solution, tracking solutions.
Excuse me?
Okay, it seems that he is ready to present. Let's welcome the speaker.
So hello everyone, welcome to my presentation. It's a great honor for me to be here, being able to present our work called RoomRecon. So I'm Seok Kim, and then our work, as the title says, it aims to create a virtual replica of indoor spaces using mobile devices. So we have a lot to cover, so let's get it started. So in this presentation, I'm firstly gonna cover background and problem statement, after which I'm gonna talk about the method and results. And finally, I'm gonna talk about the future work to guide the future researchers to carry on my work. So let's talk about the background. So in the past few years, there have been a significant advancement in technology, both in hardware and software. And then it's allowing users to capture the indoor spaces with efficiency and ease. And then these technologies are entering our mobile devices. So literally anyone can use their phone to scan their indoor spaces. And then this phenomenon can benefit a lot of different industries, such as gaming and entertainment, such as metaverse and interior design. But still, there are several problems. And many problems exist, and I cluster them into 3 different clusters. One is the static scene limitation. And what I mean by the static scene limitation is that once the user captures their indoor spaces, and then there have been significant changes made in the room, the user has no other choice but to recapture their room. So for example, the user wants to change the wallpaper or want to remove the bed from their 3D model. At the right moment, we cannot do that. And secondly, there is a texturing issue. Texturing is the key component that gives the realism and then depth to the 3D model. So it is one of the most important parts, but also very difficult part. And finally, it should operate on a mobile phone. So our mission is to allow users to create 3D virtual replica using mobile phone. So in this presentation, I'm gonna talk about the full pipeline that allows user performing such an action. And secondly, in this presentation, I will talk about a method that we suggested in our paper to improve the texturing. And then that method, we call it a divide and conquer strategy, which I will talk further in the next few slides. So once repeating, using the mobile devices, we try to give this layout, the room layout of an actual office environment, a realism. So our method is very long, and I cannot cover that, so I will try my best to simplify these steps. So our method consists of two main phases, one on the top and then one on the bottom. And then phase one focuses on capturing and generating mesh of the indoor spaces. And phase two focuses on texturing and further refinement of that texturing. And let's start with the first step, which is capturing. So user tries to capture the room very thoroughly in order to create a hole-free and complete mesh of an indoor environment. And for this, we help the user by providing two UIs, one showing the scanned area and the other showing unscanned area. And the second step, we start with the room layout and then the original mesh we just have captured in the previous step. And if you overlay these two geometry, there's an overlapping area highlighted in red. So, and we need to filter this out to get the filtered mesh. And for the layout, if you look closely, the vertical one currently has two triangles. By inserting evenly spaced grid points, we can get the remeshed layout. And then combining the filtered mesh and the remeshed layout, we can get the combined mesh, which is our final geometry, as you can see here. And then third step is the texture image acquisition, which tries to calculate the optimal camera position for the users to place their phones for the capturing of the textures of indoor spaces. And after we calculate this optimal camera position, we guide the user through AR to these positions. So maybe it's a bit confusing to understand. So firstly, we try to divide up these subplanes. So if you look at this left image, there's a plane AB, top-down view. And then currently, this work can be captured with one shot. But then if you look at the middle image, the world AB is not capturable with one shot. So what we do here is to split the world into two, in this case AC and BC, so that these subplane can be captured with one shot. And this is what we call divide step. And after these optimal camera positions are calculated, we guide the user using the 4 UI elements. And the first element is the target plane, outlined in white. And the second element is the arrow, guiding the user to these positions. And the third element is the 3D phone model that is floating in the space. And this is the optimal camera position. And then fourth element is the green boundary on the edge of the mobile devices that turns green from red if the user is sufficiently close to this position. So what we try to do here is to minimize the number of shots that are required to capture texture for the entire room. And also, by guiding the user, we expect that the user stays stationary in the moment of capture so that we can get a sharper texture images. So let's see it in action. So you see the arrow, and you see the 3D floating phone, and then the user just have captured. And moving on to the next position, the user stays stationary, capturing the texture for the world. So from the mesh processing step, which is step 2, we obtain the combined mesh. And from the step 3, we cultivated some texture images. And by texturing the geometry with the images, we can get the textured mesh. And then these textured mesh are rendered so that these 3D geometry can be converted into 2D image counterparts. And this is a very critical step, very crucial step, because now we don't have to worry about 3D anymore. We can edit the texture in 2D image space. So moving on to post-texturing, once repeating, thanks to the plane-to-image module, modifying and refining textures of the indoor spaces boiled down to simply refining and changing images. And this allows application of deep learning-based image inpainting, such as deep learning image processing methods, such as image inpainting, or stable diffusion, which is a very hot topic these days. So let's see image inpainting in action. So if you look at this wall, you can see a black areas, which is essentially an untextured area due to the occlusion from the furnitures. And for this specific case, there were sofas and chairs obstructing the view. So using image inpainting, we can efficiently fill up the texture for this room. And for the second example, the texture is already very good, showing a very clear texture. But if you look at the bottom left, there's a minor texture artifact, which is effectively solved by image inpainting as well. And finally, the most extreme example, that there's an untextured area, and also there's a major texture artifact. And the image inpainting is very effective in solving this issue. And what about the floor and ceiling? In the previous slide, all those walls that I showed are the vertical walls. And for the floor and ceiling, we provide a UI for the users to capture a sample of a floor or ceiling. And we repeat this sample in order to fill up the entire floor and ceiling area. And this is what we call a sample mode. Before I show you the result, quantitative results, I need to tell you 3 questions that we tried to answer. Did the texturing quality improve? Secondly, did the captured image show clarity or sharpness? Third point is, does it operate on a mobile phone? For this, we compared our texturing method against 3 other texturing methods for 4 metrics. And you can see that our method shows superior result for all the metrics compared to the 3 other texturing methods. And also, if you compare the blurriness of the captured images compared to the original images, it shows 0.25, which is a significant improvement from 0.41. And finally, previously, it took 29 seconds to run the entire algorithm on a mobile phone, iPhone 12 Max Pro in this case. And because we tried to minimize the number of shots that were required, we managed to bring it down to 9 seconds. So I'll show you the qualitative results. So this is the office of my company, and you can see that it resembles it shows very sharp outlook. And this is another office environment, and this is actually my room back in Korea. And then when I got this result, I was surprised that it really does look like my room. So we obtained a really nice model, and I'm gonna show you how this model can be used. So firstly, so imagine a scenario where my friend is leaving me a gift, inside a post box, and I come back home after a long day of work, and I can check his message and a gift. So this demonstrates an AR application using the created model. And also, the VR application can be done. So I place the furniture here, and then it can be used for interior design. So I introduced the RoomRecon pipeline, and also I introduced one of the many ways that could improve the texturing for the 3D indoor reconstruction. As a future work, I aim to extend this RoomRecon into multi-room settings. And also I would like to evaluate the UI components of our method. And finally, integrating the expertise insights or experiences so that I can further improve this method would be a very good direction of research. Yeah, that's it for me. And then by scanning this QR code, you can access the paper, supplementary material, and the demo video that I submitted for the conference. Yeah, thank you very much.
What about the source?
There is no. I will think about it.
Hi, thank you for the talk and for this great work. I was wondering, how does the system work with mirrors and windows? So everything that is very shiny or see-through.
Yeah. So this is a slide that shows a potential texturing problem that occurs. And then if you look at the G, you can see the reflection. And that happens when there's a transparent, as you said, a mirror. And then there's no solution for it other than using image painting, as I showed you before. Yeah.
Okay, we have another question there.
Hi, nice work. This is Chi from Amazon. I would like to ask a question. How you handle the door problem? So basically, when you record the video, you have to open and close the door. Can your model also handle that? Because door is moving.
I think I didn't understand your question.
So basically, you recording a bunch of images and you're creating a 3D mesh from it, right? Once you're recording it, for instance, you go to another room, you have to open the door. And
yeah.
Does that give you any problem or not?
Yes, so I think how I understood the question is that for the multi-room setting, if I move to different room while the images are being captured, like what happens? That's your question, right? So what I'm thinking of doing is to integrate the start and stop button. So while the user is moving into different room and opening the door, the user has to press the stop button. And after moving, he starts again for the second room. And this process has to be repeated for multiple rooms.
Okay, thanks again.
Thank you.
Next speaker. Yeah, you have to set up. You are Jin?
Yes.
Yeah. Next speaker is Jin from University of Tokyo. The title is Immersive Authoring by Demonstration of Industrial Procedures. Are you ready?
Wait a minute. Okay, I think it's working. From the beginning.
Okay, let's welcome the speaker.
Thanks for introducing me, and thanks for coming and listening to my presentation about my work, mitigating latency effects on subject experience in robot teleoperation using a VR-enabled virtual spring. I'm Jin from the University of Tokyo. Nice to meet you. And I'll start from the background. So as we know, fully autonomous robots are developing in these years, but remote robot teleoperation still remains indispensable for a variety of tasks, such as robot-assisted surgery, where human expert knowledge is still necessary, or rescue robot, where the environment and task can be very complex and unpredictable, and human intervention is always necessary. And since we are talking about teleoperation, the impact of latency is always an inevitable topic. According to previous studies, latency could have the following negative impacts in this context. And it can reduce task performance, reduce sense of presence, increase discomfort, and increase cognitive load. So it is very important for us to find a way to combat this. And fortunately, we have many excellent previous works that try to compensate for latency. And they can generally be classified into the following two categories. The first is what we call prediction-based methods. And I have listed two examples here for your reference. And the first example is the well-known predictive display, where the future states of robot and environment after each command can be predicted and displayed to the operator. And the second example is human intention intervention, where a model of human operator behavior can be constructed based on the input pattern, some body motion, or some head motion, eye gaze, a lot of information like that. Based on that, we can predict the human intention at a certain point and give the command before the human operator even reacts. So there's one problem, fundamental problem regarding this method. That is, it could be easy to predict future robot states based on this dynamic model, it's usually very hard to predict the interaction with the environment or to predict human intention based on different tasks. So it is useful, this method is generally useful for specific tasks, but can hardly be a one-size-fits-all solution. So the second method is what we call automation-based methods, and we also have two examples here for your reference. And there's a big reservoir of this kind of methods, but I just listed two very typical examples. The first is that shared control, which recognizes the fact that part of the command can be generated by the robot itself, especially some lower level ones, and human operator can need only give some higher level commands to perform the certain task so that the impact of latency can become less significant. And the second example is called learning from demonstration, where the operator can receive feedback from the environment of the remote robot and perform a demonstration, which can be later learned by the robot so that the operation essentially becomes an offline one. So in this case, the latency problems can be less significant. And also there's a fundamental problem with this kind of method, and that is it basically relies on robot automation. If the robot is not automatic enough for certain tasks, it cannot be used. And also, the possible operations will only be limited to those that can be performed by pre-designed commands. This can greatly limit its flexibility and functionality. Sometimes we want to control the robot on our own instead of relying on its automation. So here's the problem. As we can see, it is difficult to completely compensate for latency. At least there is no one-size-fits-all solution. So here we are considering an alternative. So how about we do not compensate for latency, but mitigate its impact on subjective experience? Remember that in the previous slide, I just mentioned that the impact of latency is not only on objective metrics, it can only include some subjective experience metrics, including the sense of presence and comfort level as well. So if we find a way to mitigate this impact on subjective experience, it could also be a great help for operators under high latency, in addition to some methods that can compensate for latency. So how do we do that exactly? Here's a hypothesis. If we, Okay, so if the robot movement under high latency appears more natural, the negative impact on subject experience can be mitigated. So how do we make robot movement under high latency appear more natural? So this is what I propose in this study. We are using visualization and haptic design to generate a context in which the robot movement under high latency makes sense to the operator. So here's our proposed technique based on the introduced concept. When teleoperating a robot under high latency, the robot cannot follow the target position in real time, and there will always be a position gap between this target position and actual position. This makes robot movement appear unnatural to operators because there will always be an annoying position gap, and this can limit their flexibility and make them feel very weird. So what we're doing here is that we first represent the robot and the surrounding environment in virtual reality, like what is shown in the left graph. And there's an actual position, which is an effector, and target position, which is our controller that shows the target position. And we attach a virtual spring to this position gap and add controller vibration, whose intensity is proportional to the length of the virtual spring, which corresponds to actual spring dynamics, and to simulate spring force feedback. So exactly how it will look like and what the spring does, actually. Okay. Yeah, well, if you look at the GIF on the left, you may find it looks like that the robot is really dragged by this spring, like you are really dragging this spring in reality to move this robot. And why is this the case? Well, this is because that movement of the robot under high latency actually resembles being dragged by a spring. If you look at the right GIF, you'll find that the two pictures, two GIFs look very similar. And I know this is not physically identical, but since we are talking about human perception here, and it's well known that human perception has many tolerances and imperfections that we can exploit. So as a result, operators will likely interpret this position discrepancy as spring dynamics. And we hypothesize that this could let operators find robot movement under high latency to be more natural. So here's our framework in a nutshell. First, there is a robot on the remote side, and there is network latency between this remote side robot and the operating side, where the operator is located. And we represent this robot and the surrounding environment into a virtual scene inside a virtual headset, and virtual reality headset. In this case, we are doing it in VR, and we are using VR reconstruction, but arguably it can also be an AR application or IMAR application, and they are not yet evaluated, but it is definitely possible. After this, the operator can use the controller to drag the robot in the virtual scene, and the spring will be rendered between the operator's hand and the virtual robot. Controller vibration will also be presented based on the length of the spring. So this is our framework, and we did a user study to evaluate the effectiveness of this system. Specifically, we want to evaluate whether the spring and controller vibration were indeed effective in this context, because teleoperating robot in VR itself is nothing new and has many variants already. So our original point are just is the existence of this spring and the controller vibration feedback. So to evaluate that, we adopted a 2x2 factorial within subject design and designed 4 conditions varying the existence of spring and controller vibration. So we want to see their respective main effects and interaction effect. And here are the hypotheses that we are trying to evaluate in this study. The first hypothesis is that the proposed technique can make robot movement under high latency appear more natural and less strange. And if this can be confirmed, we want to know whether this can indeed improve the subjective experience of operators. So this is hypothesis 2. And if this is also possible, we also want to know whether improving subjective experience in this way can actually have any substantial effects on some more application-based or more objective metrics, such as task performance and task load. So based on this hypothesis that we're going to evaluate, we designed the following metrics. The first is the strangeness of robot movement to evaluate this hypothesis 1, and discomfort presence to evaluate hypothesis 2, and task performance specific workload for hypothesis 3. And there's a semi-structured interview at the end. So here's our task design used to evaluate this hypothesis. And so the important thing here about this task design is that we cannot just make the task too simple. Otherwise, the participants can get used to the task and latency very quickly. So if that is the case, we can never get any results. We can just get used to the latency. And also, we cannot just make the task too complex. Otherwise, there will be too many random factors, and it will require much more participants to join the study. So it is technically not possible for us. So finally, we design a task like this. There's a cube moving among 3 fixed points on a mat in a predefined order. And the cube can change its velocity over time, every time it passes one of these 3 points. So this is to add some randomness. And participant has to teleoperate the robot to follow the cube as close as possible. And the task performance is evaluated using average following error during each trial. So here are the results. We only confirm, for strangeness of robot movement, we only confirmed the main effect of spring, but not of vibration or interaction effect, which means that the spring does make the robot movement appear less strange, and vibration does not seem to have any significant effect. And according to our interview, we get some information about this. Many participants reported that spring helped justify the robot movement, but control vibration did not meet their expectations. This kind of makes sense because control vibration does not really have direction. So no matter where and how you drag the spring, you always feel the same kind of feedback, which does not look intuitive to many people. As a result, we found that hypothesis 1 can be confirmed only for spring. And then it's about the subjective experience, including discomfort level and presence. And we also found main effect of spring only, which means that operators generally found that feel less discomfortable and more present while the spring is there. And the vibration does not seem to have a significant effect as well. This confirmed hypothesis 2 for spring as well, which means that making robot movement more natural in this way does improve subjective experience. As for vibration, since it does not even meet hypothesis 1, it is kind of reasonable that it cannot improve subjective experience in this way. As for task performance and workload, we did not find any main effect or interaction effect, unfortunately. So hypothesis 3 is not confirmed in this case. And we hypothesize that this is probably because that this task does not require any cognition, since it's just a target following task. But If we are going to use a very complex task, there's, as we mentioned before, there'll be too many random factors that make the experiment less controllable. So in the future, anyway, we are going to conduct field tests to validate this method in some real applications. So we believe that results there should be more persuasive and convincing on whether this technique can bring any substantial objective results as well. So our future directions will be, first of all, to try haptic devices or techniques that provide directional feedback, because the control of vibration in this case is not satisfactory enough. And the second step is to evaluate the framework using some real-world tasks that require more cognition. So this can be more important if we're considering to use this technique for some real applications. And the third step is to expand this concept to more types of robots. In this case, it's only a rocket arm, but it can also work on GGV, arguably, and movement, such as 60UF robot, or display, such as AR, MR. Okay, thank you for listening, and any questions will be appreciated. And just by the way, I just want to mention that we're doing a demo session in Skyview Ballroom as well, so feel free to join after this session if you are interested, and you can control a real robot located in Japan. Thank you.
Any question?
Etienne Bayer from IMT Atlantic France. Very nice talk. I would like to know what are the latency you tried, and what's the maximum range you can imagine we can use with this kind of representation, like up to a few seconds maybe? Would it make sense?
Yeah, in this case, in our study, we tried 200 milliseconds, but we personally tried 400 and still works, but above that value, it kind of feels laggy and does not really meet our expectations.
Thank you for the talk. Myung-Ori from South Korea. I may miss the part, but how did you render the vibration?
Vibration is not rendered; it's generated by the controller.
Yeah, I know, but like when did you add vibration? Like in what part of the control?
It's using control vibration, and it's generated when there's a position discrepancy, which is when you drag the spring. Based on the length of the spring, you will get the same amount of haptic feedback.
So the vibration intensity is controlled when the distance is further?
Yeah, exactly.
If it is smaller, then the vibration intensity is lower?
Yes.
All right, I see.
Thank you.
Okay, let's move to the next presentation. Let's thanks again.
Thank you.
Last presentation. The presenter is Vahid Pooryousef. The presentation title is Collaborative Forensic Autopsy Documentation and Supervised Report Generation using Hybrid Mixed Reality Environment and Generative AI. Do you have a slide? Can we have a slide? Do we have a problem again? Okay.
This shows my note.
Okay, let's welcome Vahid.
Thank you. Thank you for the introduction. Good afternoon, everyone. My name is Vahid Pooryousef from Monash University, Australia. I'm presenting collaborative forensic autopsy documentation and supervised report generation using a hybrid mixed reality environment and generative AI. While forensic autopsy is a highly specialized field, I hope you find some of the concepts and ideas presented in this work applicable to your interest areas, particularly within medical applications. So first, I want to talk about the background about what is forensic medical investigation, which also known as medical legal investigation or cause of death investigation, which is a complex process involving multiple departments working together to determine the cause of death. Here you see a workflow of the institution we're working with. The process begins with a reportable death, which requires the investigation. The admission starts with a full body CT scan. Through meetings between forensic pathologists and coroners, it will be decided whether a full autopsy is needed or a brief inspection. Half of the cases are sent to autopsy, which is a key part of this process. An autopsy is a surgical procedure, which is a surgical procedure that involves body dissection and examination of internal organs. Each autopsy can take around 30 minutes to a few hours. This process can be repeated until a report of findings is compiled and the body is released. With this introduction, we see how the operation room can be contaminated with body fluids and how difficult it can be to take notes, pictures, record voice, or use traditional computer interfaces. Also, we can imagine how XR headsets can be useful. Previous work demonstrates opportunities for AR technologies for autopsy and histopathology. However, they only explored basic capabilities like floating CT slice viewers. There are only a handful of such studies, and this area is underexplored. In our previous work presented at CHYERIM 23, we presented a feature-rich MR visualization platform for autopsy. This was only possible with close collaboration with the Victoria Institute of Forensic Medicine in Melbourne, Australia. In this work, we focused on 3D visualization and manipulation of medical imaging data, which, despite its demonstrated usefulness and suitability for autopsy, this only supports a small part of the workflow, but with further discussion with experts, we found that MR can be more useful beyond these obvious 3D data exploration capabilities. So in this paper and in this work, we present a further co-design process with forensic experts from the same institution to see how we can get more value from mixed reality across the entire workflow. This is followed by a step-by-step design and evaluation process consisting of 2 feedback sessions and 1 final study in order to shape and refine our ideas early. We developed high-fidelity prototypes to validate our design choices in stages and iterations, making it easier for the end user to understand the possibilities and capabilities of MR technologies. I'll talk about the final study results later, but the outcome of 2 feedback sessions briefly is we should use MR not only for immersive analysis and access to data, but for demonstration and data management with hands-free interface, camera, microphone, and possible integration with new AIs to automate some parts of the workflow. So we used our previous work as the foundation and designed and developed 2 additional parts. First, documentation and data collection within hybrid mixed reality, and second, generative AI plus desktop report editor. I'll go through the components of each part next. So the key component of the MR environment that we've developed is called Shadeboard. Shadeboard is a 2D wall projected display and a space for collecting, organizing, and sharing data. It is also designed for externalization of the collected data and reducing cognitive load. It provides a pop-up city window. So here, pop-up city window for higher resolution, as well as displaying out of field of view of MR headset. It also supports far mid-air interactions with drag and drop style to add, sort, and delete data elements on the board. It provides capturing photos with a simple voice command, and the location and direction of the captured photo in the MR environment are recorded. It also provides real-time voice transcription in line with photos and city images. this also supports multi-users. As you see on the bottom left corner, the user has a personal MR environment while they can collect, share, and manipulate data on the same board. We also call the board an interactive report. So with dragging and dropping each element on the board, user can play back the process with an avatar and can control the time and also hear the recorded audio. For this, no extra action needed, and it captures all the data on the go, including movements, interacting with virtual elements, captured photos and city slices with their respective location. Finally, the supervised report generation editor, which has features like visual links from sources like voice transcriptions to summaries and vice versa. It also automatically embeds city images and photos to the related parts of the report with AI. And of course, it supports manual editing. And also, it has some features like human in the loop enforcing information extraction with AI. And it also tracks all new AI-generated information and enforces human validation. It also has some AI-powered details on demand for less or more details and explaining terms in simple words for lay people with AI. And then a well-formatted autopsy report with link to figures is generated. Currently, due to the cumbersome process of finding relevant figures, only few are referenced and not even linked in the reports. So you can see how faster the process can be. So for the final study, so we had two initial feedback sessions, but this one we call it final study, which is still considered preliminary. So we ran qualitative, semi-structured interviews with 6 forensic practitioners or forensic pathologists and other expertise through video demos. In our questions, we focused on possible use cases, impact on autopsy workflow, and improvements for each component and the entire system. In this study, we didn't focus on usability of interactions in this study. Also, we did semantic analysis and classified the responses into 12 criteria. As you can see here, in this table summarizes participants' feedback and shows their strengths and weaknesses and neutral comments for each component against criteria, also color-coded with blue, red, and gray, respectively. In short, I can, do you see the, no. So on the bottom left and right, you can see the real autopsies. So in short, I can say shared board and supervised report generation favored more, and especially for actual autopsy or real autopsies. But multi-user documentation has been seen more useful for consultation and teaching, so maybe the third from the bottom. And then playback with avatar is also useful for teaching, but receive more critical comments regarding privacy and legal consequences. And also here are some quotes from the participants, like some participants think that it removes the need for photographers, or it's better because it's from the pathologist's point of view, because with the capturing photos, and it also is a more modern way of producing autopsy reports in a more organized format. And for playback with avatar, some participant thinks that verifying the pathology it can be used for verifying the pathologist have covered all necessary aspects. And on the other hand, some believe that it has extra responsibilities and focus on movements rather than findings. And another participant thinks that many of these features are nice to have, but not necessary, as many people do fine without them. So as a discussion, I want to say we discussed several impacts and findings in the paper, but some of them are first, MR documentation and report generation streamlines autopsy workflow and save time, and it also has potential to reduce cognitive load and errors because of the externalization and real-time validation. And also, maybe one of the most important point is embodied interaction provides a natural interface for AI instead of giving text prompts. So we also identify some human factors in the results. First is user resistance to changes. As we've seen in the previous slide, the person mentions it's nice to have, but we do fine without them. So, or who benefits from the technology, especially for playback with avatar? We receive many negative comments about privacy and an additional responsibility against them. But on the other hand, it can be positive thing from client's point of view. And just a very quick conclusion is we co-designed the system to streamline not only data analysis, but documentation and autopsy report generation with MR and AI. We faced several technological limitations, like centralized AI because of the privacy, hallucination of AI, and the MR headset form factors. We think that this study was preliminary, but formal and controlled studies are needed for real autopsy, which has some ethical and difficulties, so was beyond our scope. Thank you very much.
Thank you. Any question or comments? The playback with the avatar is pretty much interesting, but at the same time, that might be challenging task. Is there any complaint about the playback with the avatars?
Yes, actually, the most complaint was about that one. So if I come here, so we see none of the comments are positive, all are red or at least gray. But as we said, is one of the human factors. Mm-hmm. Who benefits from the technology? If that's the user or the pathologist, maybe it's not good for them, mm-hmm. but for clients or people that their families are, examined, so they prefer to be, the transparency of this mm-hmm. process.
Okay. Yeah. Any other comments or question? If not, let's wrap it up, and then you can catch him during the break. Thank you for all participants and presenters. Enjoy your break. Thank you.
Thank you.